Welcome to this presentation on system design for large-scale systems. Today we will be exploring the challenges and key considerations when building systems at scale like those used by Facebook and Google. Let's dive in. Here's the agenda for today's presentation. First, we will discuss the challenges of building systems at scale. Then we will dive into key design considerations for large-scale systems, followed by an example of how Facebook handles system design. Finally, we will conclude with some takeaways. Let's get started. Building systems at scale is no easy. We need to handle massive traffic loads, ensure data is distributed effectively across servers, and manage system consistency. We also have to think about fault tolerance to ensure that the system stays up and running even in the event of failures. Let's take a closer look at these challenges. First, let's discuss traffic handling and load balancing. When we are dealing with millions or even billions of users, it's crucial to distribute traffic evenly across multiple servers. Load balancing techniques such as round-robin, least connections, and weighted balancing are used to ensure that no single server is overwhelmed. Systems like Google and Facebook employ complex algorithms to manage their traffic effectively. Next, we have distributed data management. Large-scale systems must store data across multiple servers and data centers. This is achieved through techniques like sharding, which divides the data into smaller parts, and replication, which ensures multiple copies of data for reliability. Many modern systems use NoSQL databases like Cassandra to implement these strategies. Now let's talk about the CAP theorem. This theorem states that in a distributed system, you can only have two out of three qualities: consistency, availability, and partition tolerance. Most large-scale systems like Facebook and Google prioritize availability and partition tolerance, often sacrificing consistency for better user experience and uptime. Fault tolerance and high availability are critical in large-scale systems. We achieve fault tolerance through redundancy, keeping multiple copies of data across different servers. If one server fails, another can take over. This ensures that the system remains available even during hardware or network failures. Latency and performance are also key factors. Users expect real-time access to their data, so minimizing latency is essential. Techniques like caching using systems such as Redis or Memcached help reduce the load on databases and speed up response times. Content delivery networks or CDNs are also used to deliver static content faster. Security and privacy concerns are paramount, especially when handling sensitive data. Large-scale systems implement encryption for both for data both in transit and at rest. They also use strong authentication and authorization protocols such as two-factor authentication to protect user data and ensure compliance with laws like GDPR. Let's move on to key design considerations. When building large-scale systems, we need to think about scalability, both vertical and horizontal. Modular design through microservices makes the system easier to maintain and scale. Event-driven architectures help ensure high throughput, and monitoring systems provide insight into the health of the system. Scalability is a major consideration. Vertical scaling involves adding more resources to a single server, while horizontal scaling involves adding more servers to distribute the load. Horizontal scaling is often preferred for large-scale systems as it allows for greater flexibility and redundancy. Modular design through microservices is another important consideration. Instead of building one monolithic system, we break it down into smaller, independent services. This makes it easier to develop, deploy, and scale. Google is a prime example of a company that uses microservices to handle its massive infrastructure. Caching plays a huge role in reducing load on databases. By storing frequently accessed data in memory, we can speed up response times and improve system performance. Redis and Memcached are popular caching tools used in large-scale systems. Event-driven architecture is another design consideration. In this model, services communicate asynchronously through events. This allows for better handling of high throughput scenarios like real-time notifications or messaging. Many systems, including social media platforms, use event-driven architecture to deliver updates quickly. Monitoring and observability are key to ensuring system health. By tracking metrics like response times, error rates, and resource utilization, we can detect problems early and ensure that the system runs smoothly. Tools like Prometheus, Grafana, and the ELK stack are commonly used for monitoring. Disaster recovery is all about ensuring that the system can recover quickly from failures. This involves maintaining data backups and implementing failover systems. Cloud services like AWS and Google Cloud provide disaster recovery options to ensure business continuity in case of system outages. Now let's look at an example of system design for Facebook. Facebook handles massive amounts of traffic every day, so it uses load balancing to distribute user requests across multiple servers. Data is stored across multiple locations using sharding and replication, and caching is used for quick access to user profiles and posts. The system is designed to handle real-time updates and notifications, ensuring a seamless user experience. In conclusion, building large-scale systems requires careful planning and consideration of factors like scalability, performance, security, and fault tolerance. The real-world example of Facebook highlights how these principles are applied to handle millions of users globally. By following these best practices, we can design systems that are robust, scalable, and efficient. That concludes the presentation. If you have any questions, feel free to ask. I will be happy to answer. Welcome to the presentation on high-level design for a healthcare system. In this session, we will explore how to manage patient data, ensure HIPAA compliance, and implement real-time monitoring of healthcare systems. Let's get started. Healthcare systems are complex, requiring robust management of patient data, adherence to compliance standards like HIPAA, and real-time monitoring. This design focuses on ensuring secure and efficient data flow while prioritizing patient privacy and operational effectiveness. A healthcare system consists of four main components: patient information management, HIPAA compliance, real-time monitoring and alerts, and appointment scheduling and management. Each of these elements plays a critical role in ensuring a seamless, secure, and effective healthcare service. Patient information is crucial to the healthcare system. It includes personal details such as name and contact information, along with medical history, allergies, surgeries, and test results. Access to this data is controlled via role-based access, ensuring that only authorized personnel can view sensitive information. Data encryption is employed to safeguard patient confidentiality. HIPAA compliance is essential for maintaining the privacy and security of healthcare data. It involves the use of data encryption both at rest and in transit, detailed audit logs to track who access the data, role-based access control (RBAC) to ensure that only authorized users can access specific data, and secure data retention practices. Real-time monitoring is critical in healthcare for tracking patient vitals such as heart rate, blood sugar levels, and more, often using IoT devices. Data from these devices is streamed and processed in real time. Critical alerts are generated for immediate attention, ensuring that healthcare professionals can act promptly in case of emergencies. Patients and healthcare providers can schedule appointments through an online system which is integrated with doctors' availability. Automated reminders via SMS or email help reduce no-shows. The system also supports telemedicine, enabling virtual consultations between patients and doctors. This diagram outlines the high-level architecture of the system. The front end includes a patient portal and doctor's dashboard. The backend consists of APIs, databases, and authentication systems. Real-time data processing is crucial for handling live data streams from IoT devices and other sources. The front end of the system provides two main interfaces: the patient portal, where patients can view records, book appointments, and receive alerts, and the doctor's dashboard, which allows healthcare professionals to access patient records and respond to real-time alerts. The system is designed to be mobile-friendly for easy access. The backend architecture ensures smooth operation by managing databases, APIs, and security features. For data storage, we use robust databases like PostgreSQL and MongoDB. We also implement security measures such as OAuth2 and multi-factor authentication to ensure that only authorized users access sensitive data. Real-time data processing is key to handling the massive influx of data from IoT devices. We use tools like Apache Kafka and AWS Kinesis for data ingestion. Apache Flink and Spark streaming process in this data to detect patterns, while InfluxDB is used for storing time series data from patient monitors. Building a scalable and secure healthcare system comes with its challenges. Data security is addressed through encryption, RBAC, and MFA. Scalability is achieved by using cloud infrastructure and microservices. Data integrity is ensured with regular checks and backup procedures, and latency issues are mitigated using event-driven architectures and caching systems. The system relies on a wide range of technologies. For the front end, we use frameworks like React and Vue.js. The backend is built using Node.js, Django, or Spring Boot. Real-time processing is handled using tools like Kafka, Kinesis, Flick, and Spark. The technology stack ensures robustness, scalability, and security. As we look to the future, machine learning can be integrated to predict health risks based on real-time data. Interoperability with other healthcare systems will be crucial for seamless data exchange, and a mobile app can provide more convenient access to health data for patients. To conclude, this healthcare design focuses on delivering a secure, scalable, and HIPAA compliant solution. The integration of real-time monitoring, IoT devices, and data analytics will enable healthcare professionals to make informed decisions, enhancing patient care and operational efficiency. Welcome to this presentation on the high-level design of an online marketplace. In this session, we will walk through the architecture, key components, and design considerations needed to build a scalable, secure, and efficient marketplace system. An online marketplace connects buyers and sellers, enabling them to exchange products or services. The core functionality includes managing product listings, orders, payments, and reviews. Our design will emphasize scalability to handle large traffic, security to protect user data, and a seamless user experience to ensure ease of use. The system has several key components that enable it to function efficiently. These include the product catalog, user authentication and profiles, shopping cart and order management, payment transactions, user reviews and ratings, inventory management, shipping, notifications, and an admin panel. Each of these components plays a crucial role in ensuring the marketplace runs smoothly. The product catalog is the heart of the marketplace. It stores detailed product information in a relational database, ensuring efficient search and retrieval. To provide fast search capabilities, we can integrate Elasticsearch and organize products into categories for easy navigation. User authentication allows both buyers and sellers to access the marketplace. We can use OAuth 2.0 for secure login, enabling users to log in via third-party services such as Google or Facebook. Seller profiles allow them to manage their product listings and track records. The shopping cart allows users to add products before checking out. Order management handles the entire order life cycle from checkout to payment processing and shipping details. Users can track their order status in real time, ensuring transparency and customer satisfaction. Payment gateway integration is crucial for handling financial transactions. We can integrate platforms like Stripe or PayPal to process payments securely. An escrow system can ensure that payments are only released to sellers once the transaction is completed, providing protection for both parties. User reviews and ratings help build trust within the marketplace. Buyers can leave feedback based on their experience, which can be moderated for authenticity. The rating system ensures that trusted sellers are highlighted and poor performers are flagged. Inventory management allows real-time tracking of product availability. This system ensures that sellers can update their stock levels and buyers are only able to purchase items that are in stock. We can implement multi-warehouse support to optimize shipping efficiency. Shipping and delivery are integrated into the checkout process. Users can select from various shipping options with costs calculated dynamically based on their location and product weight. Integration with couriers like FedEx or UPS ensures smooth delivery management. Notifications are essential for keeping users informed about their orders, payments, and shipping status. We can use email or SMS notifications to provide real-time updates, ensuring users never miss important information. The admin panel is a powerful tool for marketplace management. It allows admin to oversee users, products, and orders, generate reports, and analyze performance. This feature helps maintain smooth operations and manage any issues that arise. When designing a system of this scale, several considerations are critical. Scalability ensures the system can handle millions of users. Reliability is achieved with failover and backup strategies. Security is paramount, utilizing HTTPS encryption and fraud prevention. Finally, performance optimization using caching and CDNs will enhance user experience. Third-party integrations play a significant role in expanding the system's capabilities. Payment gateways like Stripe and PayPal handle secure transactions. Shipping providers like ShipEngine streamline delivery, and services like Twilio and SendGrid enable communication via SMS and email. User experience (UX) is a key factor in the marketplace success. A mobile-friendly design ensures users can shop on the go, while easy navigation allows for quick product searches. Detailed product information with high-quality images and descriptions helps users make informed decisions. The flow of operation in the marketplace is straightforward. First, users visit the marketplace and browse the product catalog. Then they add products to their cart, proceed to checkout, and make payment. Finally, the seller ships the product and the buyer receives their order. This simple, efficient flow ensures a smooth shipping experience. In conclusion, the design of an online marketplace needs to focus on scalability, security, and user experience. By integrating third-party services for payments, shipping, and notifications, and considering essential system design aspects like performance and reliability, we can create a robust platform for millions of users. Thank you for your attention. We would now like to open the floor for any questions or discussions on the design and implementation of this online marketplace. Feel free to ask for clarification on any aspect. Welcome to this presentation on the high-level design for a file storage system. Today we will explore key components of such a system, the challenges involved, and strategies for achieving scalability, security, and redundancy. Let's start by outlining what we will cover today. First, we will discuss the key requirements for a file storage system. Then, we will dive into the system components, scalability, and security considerations. We will also explore file retrieval, handling large files, versioning, and monitoring. Finally, we will summarize everything. A file storage system must meet several critical requirements. First, it needs to support a wide range of file uploads, from small documents to large videos. Data redundancy is also crucial for availability, ensuring the system remains functional even during failures. Scalability is vital, especially when managing millions of files across vast storage systems. Security plays a central role involving encryption, authentication, and access control. Finally, we need to maintain good performance with fast uploads and downloads, while ensuring data consistency and metadata storage for efficient file management. Now let's break down the system components. The client interface is responsible for enabling users to upload, download, and manage their files through APIs. The upload service handles the file uploading process, including validation and background tasks. The storage service is where the actual files are stored, often using object storage, or block storage systems. To ensure durability, redundancy and backup mechanisms are implemented, like file replication and eraser coding. Finally, the distributed file system ensures scalability and fault tolerance with systems like HDFS, Ceph, or GlusterFS. Scaling the system is key to managing large volumes of data. Horizontal scaling involves adding more servers to handle increasing demand. We also use sharding, where files are distributed across multiple servers to balance the load. Caching strategies like using CDNs or in-memory caches such as Redis can significantly improve performance by reducing access times. Security is paramount in a file storage system. We employ encryption such as AES 256 to secure files both in transit and at rest. Authentication and authorization are critical, with OAuth 2.0 and JWTs being commonly used for secure access. Access control can be implemented using ACLs or RBAC to limit who can read or modify files. Finally, audit logging allows tracking all file access and changes, providing transparency and security. Efficient file retrieval relies on two main factors: indexing and metadata. By storing metadata along the files, we can quickly look up files based on their attributes like name, size, or timestamp. CND integration helps speed up access by caching files closer to the users. Additionally, pre-assigned URLs provide temporary access links for secure file sharing and downloads. When it comes to handling large files, there are several strategies. Chunking breaks, la- Chunking breaks large files into smaller, more manageable parts for upload. Asynchronous upload allows files to be uploaded in parallel, speeding up the process. Compression reduces file size before upload, saving both storage space and bandwidth. Versioning is essential for managing changes to files over time. Metadata versioning tracks changes by using timestamps to mark different versions of a file. Additionally, object storage versioning is a feature provided by platforms like Amazon S3, allowing for automatic versioning of files as they are updated. Finally, monitoring and logging plays an essential role in maintaining the health of the system. We track storage utilization to ensure we don't run out of space. Error rates help us identify issues with uploads or downloads. Access logs track who accessed which files, providing security oversight. Monitoring replication health ensures that file copies are consistently synchronized across all servers. To conclude, a well-designed file storage system needs to offer high scalability, redundancy, and security. By leveraging distributed systems, caching, and proper file management techniques, we can build a robust solution that scales with the growing demands of users. Versioning and monitoring ensure data integrity and operational health, making sure the system remains reliable and efficient. Welcome to the presentation on the high-level design for a news aggregator system. In this presentation, we will explore the architecture, key features, and design considerations necessary for building a scalable and effective news aggregator platform. Let's dive into the details. Here's the agenda for today's presentation. We will start with the requirements and features of a news aggregator system, followed by the high-level architecture. We will then explore important aspects such as scalability and performance, security considerations, and monitoring and logging. We will also walk through an example flow of the system and conclude with a summary. Let's begin by discussing the core requirements and features of the system. A news aggregator system needs to efficiently collect articles from multiple data sources. These sources could be news APIs, RSS feeds, or web scraping. Filtering is critical as the system must categorize articles based on user preferences, such as topics or time. Furthermore, the system must deliver news in real time, ensuring users always get the latest content. Personalization is also key. The system should tailor the news experience based on the user's interests, location, and reading history. Now let's look at the various data sources that provide content to the aggregator. News can be pulled from APIs like News API or Google News, RSS feeds, and through web scraping for unstructured content. It's essential to standardize all raw data into a consistent format such as JSON, XML, or HTML to streamline processing. Next, we have the injection layer where we handle the collection of news. We can use a ETL pipeline, extract, transform, and load together and standardize news from different sources. Additionally, for real-time data streaming, we can utilize tools like Apache Kafka or RabbitMQ, which allow us to handle large volumes of incoming data efficiently. In terms of data storage, we need to decide on the appropriate technologies for different use cases. Relational databases like PostgreSQL or MySQL are good choices for structured data, while NoSQL databases like MongoDB or Elasticsearch are better suited for unstructured data or large-scale searches. We can also integrate a caching layer using Redis to enhance performance by reducing latency in data retrieval. Once we have injected the data, we move to news processing. This involves categorizing news articles, performing text processing for summarization, and entity extraction to identify key topics and names. Additionally, sentiment analysis can be applied to determine if an article has a positive, negative, or neutral tone. Data deduplication ensures that duplicate articles are removed, providing a cleaner user experience. A key component of the news aggregator system is the recommendation engine. Here we can use collaborative filtering to suggest articles based on the preferences of similar users. Alternatively, content-based filtering looks at the user's previous reading history to recommend similar articles. A hybrid approach which combines both techniques can offer better accuracy in personalization. After processing and recommending the content, we need to deliver the news to the user. This is where the news delivery layer comes into play. A responsive web interface built with frameworks like React or Angular ensures users can access news on desktops and mobile devices. Additionally, we can create native or cross-platform mobile apps using tools like React Native. Content can be served via APIs, either RESTful or GraphQL, providing flexibility and scalability. An important feature of news aggregators is the notification system. We can spend push notifications for real-time updates, ensuring users are informed immediately when breaking news happens. Email alerts can also be configured to deliver daily or weekly news summaries based on the user's preferences. Notifications should be tailored to match the user's interests, topics, and activity. Now let's discuss scalability and performance. As the system grows, we need to scale horizontally using load balancers to distribute traffic evenly across servers. Adopting a microservices architecture allows for independent scaling of services as needed. To handle vast amounts of data, data sharding can be applied, dividing the data into manageable chunks across different servers. Additionally, leveraging a CDN content delivery network can ensure fast content delivery worldwide. Security is a critical concern in any system. For authentication, we can use protocols like OAuth or JWT to ensure secure user login. Data privacy is essential, especially in light of regulations like GDPR. We should also implement anti-scrapping measures such as rate limiting, CAPTCHA, and IP blocking to protect our system from malicious users. Monitoring and logging play a crucial role in ensuring the system's health. We can use tools like the ELK stack, Elasticsearch, Logstash, Kibana, or Prometheus or Grafana for log in aggregation and performance monitoring. Setting up alerts for issues like injection failures or traffic spikes is essential to maintain uptime. Collecting matrices allows us to track the system's performance, such as response times, and ensure smooth operation. Let's walk through an example flow of how the news aggregator works. First, news articles are injected from various sources. Then they are processed, categorized, and stored. The recommendation engine suggests articles to users based on their preferences, and the articles are delivered through the web or mobile interface. Finally, users receive notifications for breaking news, ensuring they are always up to date. In conclusion, the news aggregator system is designed for scalability, real-time content delivery, and personalization. The architecture focuses on handling large volumes of data, ensuring that the system remains fast, reliable, and secure. The system can be expanded and adapted as needed to meet the growing demands of users. That concludes our presentation. I hope you have a better understanding of how a news aggregator system is designed. We are now open for any questions or clarifications you might have. Thank you. Welcome to the presentation of high-level design for a chat application. In this presentation, we will cover key aspects of real-time messaging, notifications, message storage, and other important features that make a chat application scalable, efficient, and secure. Let's begin with an overview of the chat application. The application will consist of several important components: real-time messaging, notifications for new messages, message storage, user presence features, security and privacy measures, and scalability and performance considerations to handle millions of users. Moving on to functional requirements, the chat application must support real-time messaging, allowing users to send and receive messages instantly. It should handle one-on-one and group chats and track message statuses like sent, delivered, and read. Notifications will be sent both in app and as push notifications for new messages, even when users are not actively using the app. For message storage, we need persistent storage for text and media with encrypted storage to maintain privacy. Additionally, user presence features like online offline store status and typing indicators are crucial for real-time interactions. Let's look at the non-functional requirements. Scalability is a key concern, as the system must handle millions of users with efficient partitioning and sharding of messages to maintain performance. Latency is critical for a good user experience, so real-time messaging and instant notification delivery must be prioritized. We also need to ensure high availability with redundancy built into the system to minimize downtime. On top of that, the system should adhere to strict security and privacy standards, including end-to-end encryption and authentication protocols. Next, let's dive into the system components. The client side, which could be a mobile or desktop app, will display messages, cache data locally, and manage real-time communication with the server. The backend server will handle REST APIs for user management, WebSocket connections for real-time messaging, and a notification service to push alerts. A message broker like Kafka or RabbitMQ will decouple the sender and receiver for efficient message delivery. The data layer includes user and message databases along with cloud storage for media. For real-time communication, we will use WebSockets, which provide a full duplex communication channel over a persistent connection. This allows the client and server to exchange messages instantly. As an alternative, long polling can be used when WebSockets are unavailable or unsuitable, ensuring that the system remains resilient and functional. Here's a high-level overview of the data flow. When a user logs in, they authenticate using OAuth or JWT tokens, establishing a secure session. A WebSocket or long polling connection is initiated to maintain real-time communication. When sending a message, the backend processes it and forwards it to the recipient through the message broker. Messages are stored in databases and media is uploaded to cloud storage. Notifications are sent to the recipient's device, alerting them to new messages, and older messages are retrieved through REST APIs. Handling edge cases is crucial for a smooth user experience. For example, when users are offline, their messages will be stored and delivered when they reconnect. If message delivery fails, the system will automatically retry. To handle increased load, WebSocket connections will be load balanced across servers, and the message database will be shared to ensure fast access even as the system scales. Security is a top priority for the chat application. End-to-end encryption (E2EE) will be implemented using AES 256 encryption for the messages and RSA for key exchange, ensuring that no one except the sender and recipient can read the messages. OAuth and JWT tokens will be used for secure user authentication and role-based access control (RBAC). And role-based RBAC will manage user permissions. The system will also comply with data privacy regulations such as GDPR and HIPAA and ensure that data is transmitted securely over encrypted channels like HTTPS and WSS. To conclude, the chat application will be built with scalability, performance, and security in mind. By using WebSockets for real-time messaging, ensuring data privacy with end-to-end encryption, and building a robust infrastructure for handling millions of users, we will provide a seamless and secure communication platform. This design ensures that users can engage in smooth and private conversations regardless of the scale. Welcome to this presentation on high-level design for a recommendation system. Today, we will explore key components of recommendation systems, including data models, algorithms, and scalability challenges. This will give us a deeper understanding of how these systems are designed and function. A recommendation system is a tool that predicts and suggests items based on user preferences or behaviors. These systems are critical in various industries such as e-commerce, streaming, and social media. In this session, we will dive into the core aspects of building an effective recommendation system. A recommendation system is composed of three key components: data models, the foundation of the system involving user item interactions and user and item profiles; recommendation algorithms, the brains of the system, such as collaborative filtering, content based filtering, and hybrid systems; personal and filtering ensures that recommendations are tailored to each user, filtering out irrelevant suggestions. Let's first discuss the data models used in recommendation systems. User item interaction matrix, a matrix that tracks interactions between users and items. These interactions can be ratings, clicks, or purchases. User profiles, data that tracks the individual preferences and behaviors of each user. User profile, item profiles, stores information about items such as descriptions or tags, helping to connect items to users based on their characteristics. Recommendation algorithms can be broken down into three main types. Collaborative filtering finds users or items similar to the target, offering recommendations based on others' behavior. User based recommends items liked by similar users. Item based recommends items similar to those the users has interacted with. Content based filtering recommends items based on the features of the items themselves, such as genres or keywords. Hybrid systems combines collaborative and content-based filtering to leverage the advantages of both approaches. Personalization tailors recommendations based on the user's previous preferences and behaviors. This makes suggestions more relevant and increases user satisfaction. Filtering, on the other hand, helps remove irrelevant items based on factors such as content, time, or ratings, ensuring that users only see what's needed to them. When designing a recommendation system, key considerations include data collection, which is gathering data on user interactions, item attributes, and feedback is crucial for building accurate recommendations. Data storage. For scalability, it's important to store user item data and profiles in NoSQL or relational databases. Distributed systems such as Hadoop or S3 are often used for large scale storage. The recommendation pipeline involves several stages. Data pre-processing, preparing the raw data, which may include cleaning and transforming it for use in models. Model training, training collaborative filtering models such as singular value decomposition (SVD) or using neural networks for deep learning based models. Real-time processing, real-time recommendations can be powered by streaming tools like Apache Kafka, ensuring users receive up-to-date suggestions. As recommendation systems grow in size and complexity, scalability becomes a challenge. Cold start problem. New users or items lack sufficient data, making it difficult to provide accurate recommendations. Data sparsity. The user item interaction matrix can be sparse, meaning many users have interacted with only a small number of items. Latent factor models. These models help identify hidden patterns in large datasets, improving recommendations despite data sparsity. Consider an e-commerce platform like Amazon. Collaborative filtering helps suggest products based on the shopping behavior of similar users. Content-based filtering suggests products based on item attributes such as brand or category. Hybrid systems combine both methods to improve the accuracy and relevance of recommendations, ensuring users get the most suitable products. Building a recommendation system requires several tools and technologies. Machine learning frameworks, TensorFlow and PyTorch for deep learning based models, and scikit-learn for traditional algorithms. Big data tools Apache Hadoop and Spark can be used to handle large-scale data processing. Real-time processing Apache Kafka for handling real-time user data streams. Databases NoSQL databases like MongoDB or Cassandra, and traditional SQL databases such as MySQL or PostgreSQL are used for data storage. To summarize, recommendation systems play a critical role in enhancing user experience by providing personalized suggestions. Building an efficient and scalable system requires careful consideration of data models, algorithms, and real-time processing. By combining collaborative and content-based filtering and ensuring scalability, we can build a recommendation system that adapts as our platform grows. Thank you for your attention. Now I am open to any questions you might have. Feel free to ask about the design process or any specific technical aspect of recommendation systems.